Hi, my name is Igor Zavalyshyn. I will be presenting Chaos DAG, a system we developed at UCL1 for IoT software fault tolerance analysis. This system was developed with my colleagues Thomas, Axel, Ramin, and Etienne. So first, let's describe what fault injection is in a nutshell. Here we have a diagram of pretty much any IoT device. Has three important blocks: sense, encrypt, and transmit. We start from sensing the environment. In this case, it's a heart rate monitor that will be sensing beats per minute of the heart. It will encrypt this data and transmit it to the connected phone or cloud server. Now, if we have the same device, but with an injected fault in its logic, it will operate in the following way. It will still collect the data from the environment and will try to encrypt it. But due to the fault in its logic, the results might be different from the expected one. For instance, it can output a clear text, or worse, it can output an encryption key instead. Such results can be devastating for the security and privacy of this specific device and the software components that it has. And there are a variety of reasons why such faults can occur. For instance, there are natural reasons for these faults, due to electrostatic discharge or due to interference with various electric devices. But also, such faults can occur artificially, and those faults are usually associated with various attacks. For instance, due to power glitch or directed electromagnetic pulse. There are a variety of types of faults that can be generated in a given software components. And the basic one is bit flips, which can have a devastating effect on the software performance and actually logic. There are byte zeroing, in which the bytes of certain instructions will be zeroed down. Such attacks are the most effective for the software components that implement encryption algorithms and have a certain value for encryption rounds, for instance. And by zeroing it down, we can effectively skip the encryption logic. Then there are NLP faults, which replace the instructions in a given binary with NLP instructions, effectively skipping those. And finally, there are control flow disruption faults that target changing the branch or jump instructions target addresses depending on which architecture you are working with. Here is an example of fault injection attack. As you can see on the left, we have ARM assembly code of a given encryption algorithm which has 32 rounds of encryption, and every time it finishes a single round, it will jump back to 71C address, which is here, where it will verify the current counter of the rounds and go ahead with next logic step, either running another round or finishing and going to the next instruction here. However, if the attacker will want to reduce the security of a given software, he might try to change the target address of this branch instruction to the next instruction address, which is C3C, and effectively skip the complete encryption logic. In this case, the software will run only 2 rounds of encryption and make it binary susceptible to differential analysis attack. There are various countermeasures techniques out there. First, there are hardware hardening techniques, in which the circuit board will be shielded from the effects of radiation or electromagnetic interference, or certain components on the circuit board will be made redundant just to have at least one that will be working properly if the other one will fail. There are also software hardening techniques applied to the binary, for instance, by masking the pointers or randomizing the positions of instructions in a memory. And there are also source code hardening, which can be applied on a source code directly. And that's something that we were targeting in this paper. So there is a variety of source code hardening techniques, but unfortunately there is no one-fits-all technique that can be applied to any software you're working with. And it's also quite hard to understand the consequences of applying a given hardware techniques. It's hard to predict and verify all the attack vectors that the attackers can utilize. And usually that involves a security expert to understand that and to spend quite some time to actually make the software secure. So all in all, this is a really complicated process which is usually neglected by software developers. So to ease those software developers and to simplify this process of IT software developer, we propose ChaosDAG. It's an automatic software fault tolerance analysis that allows you to grab as a given software component that you want to test, inject automatically the faults in it, run it, and then report the results. So the software will tell you what was the impact of a given fault, what was the performance of the given software component after the fault was injected, and which hardening technique was more effective in protecting your software. ChaosDAG supports 6 fault types, ranging from bit flips to 0 bytes and branch faults. It focuses on a binary level, which is important. You can provide the binary compiled for production use with all the optimizations that you might need, and effectively can be used as part of a normal CI/CD cycle. So it simplifies the process automating things. ChaosDAG was implemented in Python. It works for both ARM and x86 binaries. It has a command line interface where you can provide all the details of what you want to test and which input and output parameters you would expect. It also implements intelligent fault placement, so it will be easier to understand where exactly to place the fault. And to understand the efficiency of ChaosDAG and showcase its performance and utility for the software developers, we ran a case study. We use present block cipher implementation as an example of important software component used in IoT devices nowadays. And we used 5 common hardening techniques to test their efficiency. First, we analyzed classic loop hardening techniques, which is quite popular and it's quite basic, in which you duplicate the exit loop counters and then compare them on the loop exit. And if they fail, if they are not the same, you throw an error. Variable duplication is similar, but in this case you duplicate all the variables in the given software and compare them each time they are updated. Statement counters techniques is a more elaborate one. It implements a statement control level in which after each statement in the original source code, you verify the order of execution and also the results of execution. So it's more precise in control. Then we have a function duplication in which you duplicate sensitive function in the given software and then compare their outputs. For instance, you can duplicate the encryption logic. And finally, we have a decryption at place technique, which targets specifically encryption algorithms. So you have both encryption and decryption function running side by side, and then you compare the results before transmitting. So we had a lot of results after this case study. In terms of data leakage, we see that some techniques make things really worse. For instance, variable duplication techniques increase the number of binaries that were leaking plain text. However, other techniques actually perform well and reduce the number of opportunities for faults to leak plain text. However, as you could see, every hardening technique still provided at least one binary that was leaking plain text. So it's quite hard to prevent the impact of faults on the security of a given software. Now, in terms of faults that caused plain text leakage, there was an absolute leader, branch instruction. For all of the software hardening techniques, there were a lot of binaries that were actually injected with branch fault and were leaking plain text. But we can see that for the last three hardening techniques, as you can see, the impact was rather low. In terms of impact of faults, we see the results are different for each hardening technique, gradually reducing the number of invalid cipher as we were hardening the code from quite a lot of invalid cipher in the baseline with no hardening to overall almost zero invalid cipher in certain techniques, for instance, statement counters. And statement counters techniques was quite effective in a way that it actually produced no invalid cipher, while the techniques that were exploring the redundancy on a function level were effective in a different way. They were more secure because they were either outputting valid cipher or nothing, which is quite good. In terms of fault detection, we see that all hardening techniques had quite substantial the percentage of detected faults, but the most effective was statement level control, which was implemented by statement counters technique. In it, almost 80% of faults were detected, and it was quite good because due to statement level control, we could detect faults early in the execution process and terminate the execution before continuing. So that was quite effective, and as you can see, that was the only technique that achieved such high level of detection rate. As conclusions and takeaways, we want to say that IoT faults can have a devastating effect on IoT software security. Mitigating techniques can be quite challenging, and sometimes even selected techniques can be counterproductive. They can make the software even more vulnerable. So that's why we proposed Chaos Dark, which simplifies the life of IoT software developer. It allows you to run your software with an injected fault automatically, review the results, and choose the hardening technique that will perform better. We ran a case study with Present and found out that hardening techniques that implement redundancy on a functional level perform best. We're also proud to say that Chaos Dark is open source and is available on GitHub, and we would be happy for everyone to use it in their own projects. Thank you very much.